This is the first online talk in this semester. So today we are happy to have Professor Sven Lidin with us, and he's currently serving as a professor of inorganic materials chemistry in Lund University. He completed his undergraduate PhD from Lund University. Then he moved to ANU Canberra, Australia for his first postdoc, followed by MPI FKF Stuttgart for his next postdoc. After finishing his postdoc, he joined as a professor of inorganic chemistry in Stockholm University. There he spent maybe, I think 13 years, around 13 years, right?
So, yeah, something like that.
Yeah, around 13 years. And then he moved to Lund University. So he spent, he had several administrative experiences. So a couple of them are Dean of Science, Head of the Chemistry, Head of Inorganic Chemistry, Chair of the National Committee for Chemistry, President, International Union of Crystallography from 2018 to 2021. He also served as the Commissions of Trust in many foundations. So more specifically, he was the committee member of Nobel Committee for 10 years, and the last 3 years he served as the chair of Nobel Committee, and he published more than 250 papers in his research career. So with this brief introduction, I would request Sven to talk about the introduction of diffractions among the students. So, yeah, Sven, please.
Excellent. Yeah. So thank you very much. And please, since I will probably have some difficulty seeing you during this presentation, if you have questions that come up, you need to speak up and interrupt me. I have a little bit of a problem with getting the presentation to work simultaneously as the because at the moment you don't see anything.
No.
The problem is when I start the presentation, that blocks the screen for me. So let's see if there is anything I can do about that. Seems to be a little bit problematic. Sorry about this, because if I try to share this presentation now, I have a feeling that you're going to see it in presenter mode rather than in presentation mode.
Oh, now something is coming. Yeah, something is coming here.
Yeah, but that's.
Yeah, so I can see it, but no.
Can you see it now?
Yes. Now it's fine. Absolutely fine.
Okay, so now it's the way. But so yes, that's good. But it means that I can't see you. So I will just start, and you have to interrupt me when I'm supposed to stop.
All
so,
right.
So the title of this talk is "The Power of the Image," because I really feel that with X-ray crystallography, one of the main things is that it provides us with very powerful images, and it's actually changed the way we do material science. This is a fantastic tool. At the same time, it's a little bit dangerous because it means that we tend to study problems that allow us to use structural methods. And the most powerful structural method that we have is X-ray crystallography, which means that we tend to pick problems that lend themselves well to X-ray crystallography. And let me give you an example from the lab where I work. Organic chemists tend to change the synthesis if what they make doesn't produce crystals. So they add a methyl group here or there to actually change the problem to suit the method. And quite often this doesn't really change the question much, but it's an indication that there is a danger here when we have a very powerful method. Perhaps we are overusing it. That being said, it's the method I've been using most of my career. So let's get on with it. Just to illustrate how images are taking over science, I'm going to show you the 1 year of covers for a well-known scientific publication. And I'm going to show you 1880, 1910, 1940, 70, 2000, 2016. These are the covers of this magazine. Now note that in 1880, there was just text. As we go on in time, you find that there are a few drawn images. Going another 30 years in time, you find that all the issues have images on the cover. A little bit later in time, nothing much changes, but there is actually one cover that is in color, but it's in monochrome, it's in red. Then in 2000, everything is color pictures. And of course, beyond that, not much has happened. So you see, just by looking at the covers of Science magazine, we can see how the fact that we are able to reproduce photographic images means that we are using that possibility. And crystals lend themselves exceedingly well to presentation by images. My top image here is the giant gypsum crystals in Nica in Chihuahua, Mexico. So underground caves where crystals have formed over hundreds of thousands of years at very stable temperatures, very stable vapor pressures, to grow more than 12 meters in length and many, many tons in weight. While down at the bottom, there's an image of a Syria crystal taken by high resolution electron microscopy. And these are extremely stable microcrystals or nanocrystals. This sample was revisited 10 years after it was first taken. Same sample was put up, same coordinates were put in, and the same image was shown. So highly stable crystals, although they are absolutely tiny. You can, if you count the top of these pyramids, there are 4 spots there. So it's just 4 atoms wide. This has not always been the case. The fact that we are able to study chemistry at this absolutely fine level. So Harry Jones wrote in a book published 1913, A New Era in Chemistry. Let's open it and see what's inside. So note, we know very little about the internal mechanism of solids. We do not know the simplest laws to which solid matter conforms. We do not even know the molecular weights of the simplest substances in the solid state. We do not know what's the formula of solid sodium chloride or rock salt, or of solid water, ice. And we have no reliable means at present of finding out these simplest matters about solids. Our ignorance of solids is very nearly complete. Now, that's an interesting statement because this is 1913. And in 1895, Röntgen was sitting on the 8th of November at home, and there was nothing on the telly. So he started fiddling around with his X-ray equipment instead. It wasn't X-ray equipment at the time. It was a cathode ray tube, which is exactly like a television, but without any programs on. But as he turned up the voltage, it turned out that he got X-rays, and history was made, and X-rays were discovered. But the nature of X-rays were still debated, and it wasn't until the experiment by Lauer together with von Knippe and Friedrich in 1912 that this was shown to be, first of all, a form of light. Second of all, that it was possible to get diffraction from crystals. The image seen here is copper sulfate that was used in the experiment. For Lauer was not interested in the structure of crystals. He was interested in the nature of X-rays. And it wasn't until this method was employed in the Bragg laboratory by Henry and Lawrence Bragg, same year, so news travels fast, they used this method on sodium chloride, and they managed to solve the structure of sodium chloride. They also developed Bragg's law, which we know and love for describing what the most fundamental formula of X-ray crystallography is. After this, things went very, very quickly. One reason for the development of X-ray crystallography is the phenomenal growth of the power of X-ray sources. As you can see in this graph, at the beginning of the 20th century, the power was, well, looking at the scale to the left, this is a funny scale. So it's photons per milliradian square and millimeters squared, but it's basically flux. Starting at about 1 million, it goes up. It's a logarithmic scale, so it goes up to 10 to the 36. So there's a development there of an increase in power somewhere in the range of 10 to the 30th. This means that the experiment that the Lauers made on sodium chloride, which took about a week. Now, if you had a modern X-ray source, you would be able to perform about 1 mole such experiments in 1 second. That is, of course, utterly uninteresting. You want to do something quite different. And what we're able to do today is very much looking at things as they happen. So the study of sodium chloride by the Lauers, now that's very much like looking at this image. This is the last scene of Hamlet. And so everything is done, everyone is dead. Now that's not very exciting, just knowing that at the end of the play, everyone dies. The interesting thing is what happened in between. And that is something which we can actually study by X-ray crystallography today. And I will show you one example of where we actually see phase transformations happening in real time. But let's get back to the development after the structure of sodium chloride. So of course there was a lot of technical development, there were a lot of structures being solved, and then in 1958 we got the first protein structure, that of myoglobin. This was the result of an effort that spanned many man years, many tens of man years, if not hundreds. A lot of work went into the crystallization, the refinement of the crystals, the collection of X-ray data, development of methods to solve such a large structure, and in the end, the Nobel Prize in to Kendrick and names in 1961 for X-ray crystallography of proteins in chemistry. Same year that the DNA spiral got the prize in medicine. Now, and it took 7 more years to get the first enzyme structure, lysozyme. And this was, of course, extremely interesting because now we start to see a way of understanding the action of enzymes. What's happened since? Well, let's look at the protein database. These are the entries from March 2014, so almost 10 years ago. My plan was to put up all the protein structures that were solved in March or added to the database in March 2014. But as you can see, I sort of gave up because there's just so many of them. So it's an explosive development of new crystal structures. Now, what can we do with this? Um, the interesting thing in getting that extreme amount of information is that you get possibilities to compare things. If any of you have seen this movie, it's The Good, the Bad, and the Ugly, a good old western um, by Ennio Morricone. The interesting thing here is that Sergio Leone. The music was written by Ennio Morricone. Now, look very carefully at the gun dealer here to the right, and you will realize that he is the spitting image of Max Planck. Now, this is not information at all. This is just telling us something about hairstyles, styles of glasses, styles of mustaches, and what Europeans look like as they approach old age. So there is no real information here. It's just a coincidence. So we should be very careful in jumping into conclusions about things that look the same. On the other hand, if you look at the actor to the left, um, you will recognize he's a young man. You will recognize him as an older man in a much older movie. This is The Godfather 3, and he is Don Albarello. Uh, Same person, different ages, but it's very easy to recognize him. And now this is interesting information suddenly. We can recognize people across ages because they have some features that we're able to pick up. So, lesson to be learned here. Well, sometimes a cigar is just a cigar. Sometimes likeness doesn't mean anything. Sometimes it is very important. Now, we have a tendency to make visual contacts when we approach new images. And so at the top here are images of French actresses from the turn of last century, all impersonating the Mona Lisa. And of course, you recognize the painting. You also have the background, which is very similar, of course. But the interesting thing is that now these actresses are really trying to look like the painting, but you don't have to have that sort of likeness in order to pick up the cues. There's a famous painting by Botero where you have no problems in recognizing the Mona Lisa, although the style of Botero is shining through very clearly. And I'm sure that you recognize the Mona Lisa also in this image. So small visual clues have a large impact on what we see. And this is something that you can use as scientists, but it's also something that you have to be careful with so that you are not led astray by likenesses that really don't have any major significance for your understanding. Now, what's important to know about crystals is that quite often they are a mess. They're never really single, they're never perfect. And so we need to be careful about what goes on in crystals. If you look at the online dictionary for crystallography and look under twinning, you will find that there are many, many ways that things can twin. And this is perhaps the most common problem in crystallography, the fact that you don't have a single crystal, you have several. And I can cast your horoscope for the next coming days. If you're going to pick crystals, you are going to come across twins. Uh, of course, sometimes this is just accidental twinning. So crystals that happen to grow together, or sloppy crystal picking. So you just mount two crystals because it's finicky work to pick up a very small single crystal. But let's look at an example of twinning that's impossible to avoid. So aluminum 3, magnesium 2. To the left, you have a newly grown crystal of Al3Mg2. This is a large cubic crystal. It's got a unit cell of about 30 angstroms, so huge. And the diffraction pattern to the left is very close to compatible with the space group FD3M. However, the small dots encircled in black here are exceptions to that rule. So obviously something strange is going on here. In fact, the cubic structure of aluminum 3 magnesium 2 is not stable at room temperature, but it undergoes a phase transition to a rhombohedral form. On the right-hand side, you see the diffraction pattern from the same crystal after that phase transition has been completed by annealing the crystal at a low temperature. And you see how all the extinction conditions corresponding to a D-glide, which would give you a sort of a diamond-like pattern. If you can see my pointer, it's this sort of pattern. Now, of course, here that sort of pattern is replaced by something where also the middle dot is present, and so it's clearly primitive. In fact, it's not even cubic, it's rhombohedral, and you can solve the structure. Now, what's quite interesting is you can actually solve that rhombohedral structure from the very poor twinned data set to the left. But what you find is that the shapes of the crystals are of the atoms are very strange. You find that there are those which are large spheres. There are those which look like dinner plates, those that look like cigars. But if you anneal the crystal, this changes, and you get a very nice image of almost perfect spherical atoms, which is telling you that this is certainly the right solution. Looking again at the pre-annealed sample, some atoms are really misbehaving, but after annealing, everything looks fine. Still, what we are looking at here is a twin. It's a rhombohedral twin of 4 individuals. So in order to solve the structure, you need to know that it's a twin, and you need to treat that twin. And there are technical tricks for that, but you have to remember to look for these possibilities, because sometimes the problem that you have with poor data is that you've got twinning at the bottom. Now, sometimes things are a little bit worse because it's twinning, but it's twinning with different crystal structures. So, like another well-known film. So, a very simple example, cesium hexachloroiridate. This is the diffraction pattern. You can see that there are several different ways of finding unit cells. They all have difficulties to them. If you want to find what would be the real unit cell of a if this was a single crystal, it would be just a quarter of the blue unit cell shown here. The blue unit cell is sort of an average of the crystal structure. This can be defined in terms of 2 subcells, the green and the red, which grow together to create the full diffraction pattern. And so there are some systematic absences here, and there are some doubling of the unit cell in 2 different directions. And by indexing this as a twin, so that there are 2 different unit cells, it's possible to solve this. And we come up with the 2 possible crystal structures on the left and right here. One of them has an orthorhombic cell in white, shown in white to the left, and a rhombohedral, a monoclinic cell shown to the right. If you analyze it a little bit closer, you will see that it actually consists of 2 types of blocks, which are displaced with respect to each other in the along the line of sight in this image, so that you can look at this as a stacking of slabs, and the left stacking is AB, and the right stacking is A prime B, because the A prime block has been shifted along the line of sight. So this is a different kind of twinning, where again you have different components that make up the twin. This is very similar to what you see in the closed packed structures of metals. So magnesium is AB, whereas neodymium is ABC, ABA. It's just, there are so many ways to stack closed packed layers, and they are very similar in energy, and you find the same at larger levels. And I'll give you one more example of this. This is called allotwinning, when you have the association of crystals of polytypes growing together. And allotwinning comes from allos, which is different in Greek. So you have different individuals twinned together. So a molecular example of this is a co-crystal of sulfur diamidine and 4-aminosalicylic acid. This can crystallize in two forms, in P121A1 or PNA21. These are extremely similar, but there is again a shift along the line of sight, which allows for the left-hand structure to be monoclinic, the right-hand structure is orthorhombic. And if we make things simpler by drawing the main motif here as an ellipsoid, what you find is that these ellipses can stack at different heights, and you see the left-hand row of the left-hand structure is actually identical to the left-hand row of the right-hand structure. The second row is also the same in the two structures. It's the third row that differs, but it means that nearest neighbor interactions for all these ellipses is the same. So it's only second nearest neighbor interactions that differ. And of course, this makes things a lot easier for nature to use these different structures, so to speak, because the differences in energy are small. And the larger the object, the smaller the difference in energy, because next neighbor interactions happen at larger distances. Now, if we go to slightly more complicated structures, you can look at the structure of zinc 4 antimony 3. Now, this is a well-known thermoelectric material. Thermoelectrics have the fantastic property of being able to transform thermal motion directly into electrical flow. And this requires a structure which conducts electricity well, but conducts heat very badly. This material conducts heat like perspex, plexiglass. So why is that? Well, you can look at the diffraction pattern on the left here, which is the alpha phase, the room temperature phase of zinc 4 antimony 3. And to the right, you have the structure at slightly lower temperatures, 240 K. And what you see is the development of a slight superstructure. And that is shown in having a much denser distribution of diffraction spots. If we increase the resolution, you can see that it's actually a fourfold superstructure of the original arrangement. And if we look at what the structure looks like in reality, now this is the electron density of the alpha form of zinc 4 antimony 3. And in fact, this is not zinc 4 antimony 3, it's zinc 13 minus X antimony 10. How do you interpret this image? You can see that there are some electron densities that correspond to nice and well-behaved atoms. There are some that have handles on them. There are some that are quite faint. There's something funny going on here. Um, we can get some help by looking at what goes on at different temperatures or with doping. So I'm now going to bring in the low temperature form, the beta form in blue. And you can see that the blue electron densities, they don't quite overlap with the black ones. I'll go back and I can put this on again. So you can see that there are some of the funny shapes now become very well defined. Some of the weak features become increased in strength. You look at the central feature of two weak spots. These now become fully occupied sites. And we can also look at a doped sample where we bring in a small amount of bismuth, and that gives us this yellow structure, which is an absolutely well-behaved form of the alpha structure. So what's going on here is that the room temperature form is a mixture of two crystal structures. Let's look at what that looks like again in terms of electron density. So you have the black pattern, the blue pattern, and the yellow pattern. The black pattern is the sum, the weighted sum of the blue and the yellow. This is what the structure looks like. It's rather difficult to make out what the actual relationships are. What I want to pinpoint to you here is that the blue kind of kite-like objects, these are interstitial atoms that have ordered in the low temperature phase. And I'm bringing in from the left the fully ordered, again, the fully ordered structure that is present at in the doped form. That is actually occurring as slabs in the low temperature phase. And then there's another slab here, whereas the ordered interstitials live in 3 consecutive slabs. This is why it's a fourfold superstructure that you look at. Now, what makes this a little bit complicated is that not only is this superstructure low symmetry, it's actually triclinic. And the host structure is hexagonal, which means that you got 6 copies. But there is also an intergrowth between this and the pure phase, like in the doped crystal, so that there is a mixture of the high and the low temperature phases. Just to make life a little bit more complicated, if we cool another 10 degrees, we get the alpha prime phase, which is a really low temperature phase. And let's take a closer look at that, and you will see that you have a lot more of the satellite reflections that are showing us that we have a superstructure. If we look a bit more carefully at this, you see it's a very strange distribution of intensities. In fact, you have the main reflections, you have still the fourfold superstructure. And then on top of that, you have a 13-fold superstructure. So what happened now is that going from the diffraction pattern that we had for the room temperature phase, where we just have disordered interstitials and we have a rather simple structure, to the first low temperature phase where we have a fourfold superstructure but with remnants of the room temperature phase. We now have a 13-fold superstructure but with remnants of the fourfold superstructure, and these again grow together. That reflection is unique for the fourfold structure. Those two are clearly overlapping reflections from the fourfold and the 13-fold, and the rest, the rest are pure 13-fold phase reflections, and they can be used to solve the 230-degree structure. Again, this is triclinic. There are 6 individuals of it. It coexists with the 4-fold, which there are also 6 individuals of. The twinning becomes horrendously complex, but it is possible to solve the structure. It looks extremely similar to what we saw before. But in this case, you've got the triple sandwiches of interstitials. Then you have pure interstitial free parts. And the interesting thing here, of course, is that the top one that I was putting in from the left-hand side. So first in red here. Now the slab coming in from the left here is 1.5 unit cells thick. The second is 1 unit cell thick, and the third is 1.5, regarding the structure of the basic cell. So again, we have this strange phenomenon of 2 faces that live very close together and which share interfaces that allows us to intergrow different faces. The amazing thing is that X-ray crystallography allows us to solve structures like this. Now, when I started speaking, I was making the case of synchrotrons, which allow us to solve structures that are even more complicated because we get such a lot of data, but also to do things in real time and to resolve problems that are not possible to solve on a home source. Stistite is a mineral which is found along the banks of the river Tanama in Puerto Rico. Stistite is in fact a mixture of tin and antimony. It's got a huge existence interval. You can see from 40% all the way up to 57% of tin, you can form this interesting face. If you try to synthesize it at the 2 ends, you get rather similar but somewhat different diffraction patterns. To the left, we have a very tin poor stistite. At the right, we have a very tin rich stistite. So these were made at these compositions. So the left-hand side starting with a small amount of tin. The right-hand side, we're starting at the point of the concentrate of the composition of the sort of mystery phase SN3sB2, which is not stable at low temperatures. And when we cool that down, we get the diffraction pattern to the right. There seems to be a lot of things going on here. So let's try to analyze what this diffraction pattern means. This is a modulated structure, a structure with a periodic distortion that is incompatible with the basic lattice. So you have a basic unit cell, and then you have a set of satellites. To the left, the satellites are just running in one direction. To the right, the satellites are running in what we see in this picture is at least 2 directions. We can recognize this from the crystal structure of antimony itself. It looks quite much the same. I'll go back. You see the sort of the rectangle here, and the fact that there is a feature in the middle of it. For the cystite, this is separated into different spots. For antimony itself, it's just one central spot. And for antimony, the reason for this structure is the fact that we have alternating long and short distances along the z-axis of the rhombohedral cell. For stistite, it's actually the same. we have blocks of antimony interleaved with rock salt type structures of antimony tin. These have a composition which isn't that of rock salt 1-to-1 because of the limited size of the blocks, which is just 7 layers. So this is tin 4 antimony 3, And then there's an admixture of antimony in between. So for the 57% of tin, it's really tin 4 antimony 3 on the right-hand side. On the left-hand side, you have a much more antimony-rich sample. So there are big blocks of elemental antimony interleaving the tin antimony structure. But the question remains, what's all the garbage that we see in the tin-rich cystite? Well, first of all, you have the cystite itself. So you have in green here, you have the basic unit cell given by the stronger reflections. You have satellites running in two different directions across the unit cell. So that explains part of this pattern, but you can see that there is more. There is also a set of weaker reflections that seem to run in two different directions as well. This is elemental tin, the tetragonal form of elemental tin. So these are obviously intergrowing with each other. So we have cystite and we have elemental tin. They are perfectly well aligned. And now cystite is rhombohedral, but it's growing in a twinned form where the overall symmetry is cubic. Tin is tetragonal. This is also growing in a twinned form where you get an overall cubic diffraction pattern. But this still doesn't explain everything that we see in the pattern. There is also a lot of diffuse scattering, which is telling us that there is a lot of strain in this structure. In fact, if we leave this sample for a month on the lab bench, protected from the atmosphere, it will revert to the tin pore form. Tin is going to diffuse through the structure and get onto the surface where it amorphizes. So we get an amorphous tin layer, and the cystite becomes free of twinning. So it's really an interesting, very slow reaction. In addition to this, we also have some impurities in the diffraction pattern that come from multiple scattering. So this is just because the X-rays are not quite pure. This is a home source, and so we get lambda halves. So these are reflections that are caused by a much lower intensity part of the X-ray spectrum that is generated by the X-ray tube. And then there is also garbage. This is not a pure crystal. There are small pieces of something else sitting on the surface. This is not a simple synthesis to make in pure form. So how do we understand the fact that when we start from the high temperature form, where we have the question mark, and we cool that down, we get this funny pseudo-cubic arrangement of tin and antimony? Well, looking at what's going on around it, it's not that strange. You can see that composition-wise, we are somewhere between cystite, SNSB, and tin. So as we cool down this unstable phase, it phase separates into tin and antimony tin. But it phase separates at a temperature where diffusion is very slow. So initially, we get perfectly well aligned crystalline tin and crystalline antimony tin. The fact that it forms in a cubic, in a pseudo-cubic arrangement of crystallites indicates that the high temperature phase SN3 SB2 is actually cubic. The difficulty is that it's not quenchable. So as soon as you cool this crystal down, it changes into the two components SNSB and SN. What we thought would be possible to do is to synthesize this crystal and then to bring it fresh to a synchrotron and measure it at high temperature, because there are several issues with getting crystal structure out of this. First of all, antimony and tin are neighbors in the periodic table. So the difference in scattering length between the two is extremely small. So it's difficult to see the difference between tin and antimony. The reason we saw a superstructure in stistite is not that we really see a big difference in scattering from antimony and tin, but that we see a difference in interatomic distances, which makes it possible for us to identify what is antimony and tin. But at the synchrotron, we can tune the X-ray wavelength to a point which is close to the absorption edge of antimony. And at that point, antimony scatters a lot more than tin. And so we artificially create a structure which seems to have a large difference in electron density. Secondly, we get a lot more intensity with the synchrotron, so we can actually measure weak satellites, and we can follow things as they happen. Now, the idea was just to reheat the sample. So we make the crystal, we cool it down to room temperature, and we try to heat it up at the synchrotron. What happens? Well, the diffraction pattern that we were hoping to get back to the original phase. Now, unfortunately, what we see is to the left-hand side here is the diffraction pattern that we see at 25 degrees. You can see that it has already reverted to an untwinned state. As we heat it, the only thing that happens is that the position of the satellites changes to a very small extent. And we know from previous experiments that this just means that we have a change in composition. So what we can see is that as we go from room temperature and upwards, we are losing tin from the structure. You can see how the tin content is decreasing with increasing temperature. This means that our heating didn't really work, because what happened was instead that we follow the liquidus curve of the stistite as we heat. Now, of course, the obvious solution would be to add tin. So what we did, this was in the middle of the night at the synchrotron, we opened up our precious capillary with the crystal, we added a small grain of tin on top of it, we resealed and we reheated. And lo and behold, as we heat up the sample, we go from the rhombohedral image to this, which is in fact not twinned, but cubic. You can prove this by trying to solve the structure as rhombohedrally twinned, and you see that the fit is really poor, whereas the fit to cubic structure is really good. Now, what does it look like? Well, this is again the rock salt structure of antimony tin 121, but at the edges of small crystallites, which are 7 by 7 by 7 atomic layers, there are extra layers of tin. So the rock salt structure is not stable because of the interactions between heteroatoms and homoatoms, so that the tin atoms want to be a little bit closer than they get to in the rock salt structure. And this means that you can only build the blocks here to a certain size, and then you get a layer of pure tin. This is not completely ordered, so you get this is like an average picture. But you get the same sort of blocks that we saw for the rhombohedral structure, only in the rhombohedral structure of stistite, you had infinite layers. Here we only have limited blocks, 7 by 7 by 7, all finished off with layers of tin. I will stop there to allow you some questions. What I've been trying to show you, of course, is that things are not quite as simple as they seem. I want to point out that in my experience, about 10% of the crystals that we're actually able to see anything useful from turn out to have complications of different kinds. Twinning, incommensurabilities, diffuse scattering, you name it. Um, of course, that means that 90% of the good crystals are really good crystals. And so it's a very trustworthy method. It gives you really nice results, but don't expect crystallography to treat you nicely. It will throw you examples that are very difficult to deal with. And I have now only showed you cases where we have been able to successfully solve them. I have many cases of failure as well, where in the end we know that, well, there is something here that nature is trying to tell us, but we just don't know what it is. So thank you very much.
Thank you, Sven. Thank you very much for your talk on diffractions, and the floor is open for questions. So the students, if you have some questions, you please go ahead. Yeah, we don't have much time, so we have 5 minutes left. So if there is any question, so yeah,
Well,
yeah. So
I was crystal clear, right?
either they understand everything or they didn't understand anything.
Well, you're just starting the course, right?
Yeah. This is just the beginning of the course, and they
Yeah.
are master students. So probably they need some time. Probably they have heard about these terms, but still now they need some. I mean, they need some time to understand
Yep.
the term you have discussed. Yeah, but many times, Sven, I just on behalf of them, I can ask one question that many
Mhm.
time. I mean, the students ask that what is the reason behind the twinning? So, is there any specific reason?
There are many specific reasons, and I think some of the examples that I showed show some of them. So first of all, a very common reason is that you have a structure that is stable at high temperature, and when you cool down, another phase becomes stable. And if you think of the if you think of the normal behavior of crystals, you always have a higher amount of ordering at low temperature than at high temperature. So the reason that you can allow for a high symmetry structure at high temperature is that there is some disorder. As that orders, you lower the symmetry, which means that a high symmetry phase occurring at high temperature will revert into low symmetry structure at low temperature, but this will happen simultaneously in the whole crystal. This will nucleate. So this is like a new crystallization, but it's taking place in a clamped state where all the atoms already have their positions. They can't move far. And so you grow only small crystallites with different orientations, but they are sort of clamped by the original structure. So this is a very common case. Another common case is that you have different crystal forms that are very similar in energy. So this is typical for polymorphs. So there are several elements that crystallize as either cubic close packed or hexagonally close packed, and quite often you get intergrowths between them because the energy difference is so small. And there are other cases with polytopes where where you form very thin layers of crystals, and these are quite flexible. And what can happen is that you form a layer, say 5, 6 atoms thick, and this floppy layer meets the edge of itself and overlaps with it, and then you get growth in terms of a screw dislocation. And this can contain the fingerprint of a 5-layer or 6-layer or 7-layer structure, which then propagates throughout the entire structure. And so this is really a kind of intimate twinning where the crystal twins with itself and forms an entirely new structure with a long period superstructure because of this intergrowth with itself. So there are many reasons why twins form. I would probably want to rephrase the question, say instead, why do twins not form? because it's actually very natural for crystals to grow as twins. And as crystallographers, we do everything to avoid seeing twins. And sometimes we can find really nice growth conditions where twins do not form. And then we're happy because we get simple problems to solve. If you just leave a solution to evaporate, what normally happens is you get crystals forming. As you leave the solution to evaporate further, these crystals will grow together. So just because they're sitting next to each other and they're fighting for the same substance, they will sit there. As they grow, they can't move. As they grow together, and then you get sort of random oriented twins. So there are so many different ways that this can happen. And that's why it happens. The wonderful thing is that it doesn't happen more often.
Yeah, thank you, Sven. We are running out of time, so probably on behalf of all the students, so we want to thank you once again for your insightful talk. And probably at the end of the semester, we will see us once again. Then probably my students will understand everything what you are going to speak.
Excellent.
Yeah.
Yeah. I know that will happen. You're a good teacher.
Yeah. Thank you very much. We'll see us soon.
Okay.
Yeah.
Thank you.
Bye. Take care.